Okay, so our first topic in mathematics for chemistry is calculus. Now, calculus can be divided into two areas: the study of differentiation and the study of integration. Now, these are essentially two different mathematical operations that allow us to understand and interpret a number of physical phenomena in different ways. So, differentiation is essentially about studying rates of change. Now, in mathematics, a rate of change corresponds to taking the gradient of some function. We may also want to study equations involving rates of changes. And in mathematics, and specifically in calculus, these are called differential equations. Now, the primary use for integration is in, well, we may come to a point where we may want to add together lots of, and actually frequently an infinite number of really tiny quantities. And in mathematics that corresponds to talking about an operation called the definite integral. Now, I've just put that in there just so that I have a piece of mathematics to talk about, but we're actually going to understand what a definite integral is by studying calculus. So, don't worry if that doesn't make any sense at all. Now, integration, actually, the operations of differentiation and integration are very closely related. They're in fact inverse operations. That means if I say I differentiated some function, then I integrated it, it would be the same as doing nothing to it. They are inverses of each other, and vice versa. So if I integrated a function, then I differentiated it, it would be the same as if I had done nothing to it. And again, an understanding of that will come from study of calculus. Now, the reason I said that was because if I construct an equation involving different rates of changes, then I want to do the opposite of that in order to solve it. And so that's why integration is useful in understanding equations involving rates of change. And in mathematics that will correspond to solving a differential equation. Now, a differential equations, again, it's actually a topic on its own, but we actually need to understand calculus in order to be able to construct and solve these kinds of equations. So, studying calculus kind of sets the scene for later study of differential equations, which I will do a set of videos on. Now, another, maybe it might look like a mathematical use, but another use for integration is actually in the study of geometry. Now, I won't actually say a lot about this, but things like, I don't know, if you want to know the surface area of a sphere, so if we had a spherical particle or something, we may want to, I don't know, we may want to know its surface area. Now, that comes from elementary geometry that you may or may not have learnt in school, but you can easily construct a problem in calculus that would tell you, in case you've forgotten and don't have a book nearby, what is the surface area of my sphere. Now, I'm not going to dwell on this for too long, but just to set the stage a little, I'm going to give a few examples of where this kind of mathematics is very useful in chemistry. So, chemical examples. And the first, and probably one that you're most familiar with, is probably from A-level chemistry, or if you're American, AP chemistry, is the study of chemical kinetics. Now, chemical kinetics is, it is the study of rate processes. So, how fast is my chemical reaction going? We may want to know if we start with a specific amount of reagent, and we want to know at what time how much product will we have. That comes from constructing this, what is called a rate equation, and solving it. So that's where differential equations comes in chemistry. Another example of use of this kind of mathematics is in quantum mechanics. Quantum mechanics, where an example from quantum mechanics is actually quantum mechanics is all about a mathematical object called the wave function. Now, in quantum mechanics, we learned that the square of the wave function is proportional to the square of the wave function times a volume element, which we'll learn what that is in calculus, is proportional to the probability of finding a system in a certain state. So these probabilities are for tiny volumes in space. So we'd have to add together these tiny probabilities in order to find the probability of a system being in a state for the entire system. So adding together lots of tiny probabilities. And we did say before that integration's used for adding together lots of really tiny quantities, so that's where we'll see this in action. And the final area where calculus is useful, well, not the final, but the final example I will give is in thermodynamics. Now, thermodynamics is in fact all about, because we can't add a quantity like enthalpy from thermodynamics, we can't really, it's not really convenient to measure the enthalpy that's contained in an object. We can do computations to kind of work out what it should be, but to measure in a lab the amount of enthalpy in something is difficult, if not impossible. So we want to be, what is easy to do is to set up a system in one state and work out the energy difference between that system and a system in another state. So we would use calculus here to understand data involving rates of change. Now, all of these topics together are actually the main pillars of physical chemistry. Now, physical chemistry is, well, as you probably already know, physical chemistry is essentially pieces of physics that are useful in understanding chemistry, so it's actually very important. and the study of physical chemistry, understanding physical chemistry, is our main motivation for studying mathematics here, and so that's where I'll stop. See you again later.